Okay, so today we're going to talk about combining functions. And on the surface, it seems like pretty simple algebra, right? But believe me, there's a hidden rule that trips up almost everyone. So let's dive in. The basic idea makes total sense. We add numbers like 5 and 3 all the time, so why can't we just add functions like f of x and g of x? Well, you can. And it seems like it's going to be perfectly straightforward. But, and this is a big but, here's the catch. Doing the actual algebra, that's the easy part. The real challenge, and what we're really going to focus on today, is figuring out the domain of that new combined function. This is where those hidden rules live. So let's get the simple part out of the way first. When you see something like f plus g of x, all it really means is you take the expression for f of x and you add it to the expression for g of x. It's the same deal for subtraction, multiplication, and division. Easy enough. Okay, here's a really great way to think about this. Picture function f as a machine, and it only accepts certain things. That's its domain. Now, function g is another machine, and it has its own set of rules. So what happens if you weld them together? What can you safely feed this new combo machine? Well, only the stuff that both of the original machines could handle, right? That machine analogy, it leads us right to the single most important concept here. There's a formal rule for this, and honestly, it's the secret to getting these problems right every single time. And here it is. It's called the domain intersection rule. For adding, subtracting, and multiplying functions, the new function is only defined where both, and I mean both of the original functions are defined. You have to find the overlap, the stuff they have in common. That's your new domain. So, mathematically, it looks like this. The new domain is the domain of f intersected with the domain of g. That little upside-down U symbol just means intersection, or, the stuff they both share. All right, theory is great and all, but let's see how this actually works. We're going to walk through a real example to see exactly how to find this overlap. So let's take these two functions. F of x is the square root of x plus 2, and g of x is the square root of 3 minus x. We're going to multiply them together, but more importantly, we're going to find the domain of the result. It's a pretty simple three-step process. First, find the domain of f. Second, find the domain of g. And the final, most important step, find where those two domains overlap. Okay, let's break this down. For f of x, we can't take the square root of a negative number, right? So the stuff inside, x plus 2, has to be 0 or more. That means x has to be greater than or equal to negative 2. For g of x, same deal. 3 minus x has to be 0 or more, which means x has to be less than or equal to 3. Now for the crucial part, the intersection. We need numbers that are both greater than or equal to negative 2 and less than or equal to 3. Well, what's left? Just the numbers from negative 2 to 3. And there you have it, our final answer. The new function is just the product of the two. Sure. But the real key here, the part that matters, is its domain. The only valid inputs are in that little interval from negative 2 to 3. So we've handled addition, subtraction, and multiplication. But division, division has its own special little trap just waiting for you. And this is where things can get really tricky. Check this out. If we divide x squared minus 1 by x minus 1, you might notice you can factor the top, cancel out the x minus 1 terms, and you're left with this beautifully simple answer, x plus 1. It almost seems too easy, doesn't it? So, does that mean the new function is just the simple line y equals x plus 1? I mean, we canceled the problem away, right? What could possibly be wrong with that? Well, this is what's wrong. For division, you get an extra rule on top of everything else. The denominator can't be 0. And here's the key. This rule applies to the original function before you do any of that slick canceling. And this right here, this is the heart of the trap. Even though the algebra cleans up nicely and that x minus 1 term seems to vanish, the restriction it created, it sticks around. It persists. In the original problem, x could not be 1 because that would make the denominator 0. And that fact doesn't just go away. So what does this actually look like? Well, the graph is the line y equals x plus 1, but with a tiny single point missing. There's a literal hole in the graph at x equals 1, because our original setup was undefined there. The cancellation hides the trap, but that hole is still very, very real. So let's recap the big pitfalls to watch out for. First, the cancellation trap. Yeah, x divided by x is 1, but you have to remember that x couldn't be 0 in the first place. And second, don't forget the intersection rule. If you try to add the square root of x and the square root of negative x,
you'll find that the only number that works for both is plain old 0.
At this point, you might be thinking, okay, that's a neat math trick, I guess, but why does any of this really matter? Well, it turns out this idea of combining functions and respecting their domains, it shows up everywhere.
Let's take a real-world business example. Probably the most important function for any company is profit. And how do you find profit? It's just a combination of two other functions: revenue, which is the money coming in, and cost, the money going out.
The profit function is literally just revenue minus cost. It's a perfect real-world example of function subtraction. And of course, the domain matters. You can't exactly produce a negative number of widgets, so the inputs have to make sense. And looking ahead, especially if you're planning on taking more math, this is not just some topic you can forget about. Understanding how these domains work is absolutely crucial for getting your head around limits, derivatives, and integrals in calculus. Seriously, this is a foundational building block. So, we'll leave you with this question to chew on. We just saw that something as simple as division has a hidden rule about its domain. So, what other basic math concepts might have secret rules that you've just never noticed before?